So today we'll start with the Bohr's atomic model.
It's a screen, sir.
Yeah. I'm keeping these lectures in YouTube, huh? So
Yes.
a YouTube link also and there also. So you'll be able to check it. Bohr's atomic model. So Bohr's atomic model. So first of all, who was Bohr? He was a. Let us see this. Niels Bohr. Okay. Please know about him a little bit. He is a great physicist who made a foundation contribution understanding atomic structure, quantum theory. This is the main thing. Quantum theory is the old quantum theory is a collection of results, but the quantum theory, whatever you know, is today is attributed to large extent to this fellow. Huh? So he has won a Nobel Prize. His full name is Niels Bohr. You can know him Neil H.D. Bohr, but it's Niels Bohr. He was from. He's a Danish physicist. You should know about it. Just knowing Bohr will not do. Who is he actually? What was his real life and all? And this is what he has predicted. This is what we are going to learn today. His atomic spectra. All these relations we are going to. This is the Balmer series. You may be knowing now. Yesterday I have taught you what is Balmer series. RH is the Rydberg constant.
Yes,
This is the Rydberg. This is the Rydberg formula. We are going to see that now. Okay. H is Planck's constant. All this is what we are going to. We're going to go through it today. His picture of the atom. Clear? So
yes, sir.
let's see what he is saying. So Bohr's atomic model. So in Bohr's atomic model consists of, first thing is the nuclear concept. Nuclear concept. So the nuclear concept, he said, just like Rutherford, that there is a central core of the atom where the entire charge and mass is concentrated. So you write an atom consists of a. So just you can understand from here, an atom consists of a central core where the entire charge and mass of the atom is concentrated. Okay, the atom as a whole is neutral. Okay, an atom as a whole is neutral, means the sum of charge in the nucleus and the sum of the electrons is equals to. Okay.
Yes, sir.
So then after the nuclear concept comes the quantization concept. Now what is quantization concept? According to this concept, electrons
Sir, can you repeat?
Electrons.
According.
No, just according. No, right, according. Yeah, according to this concept, electrons can revolve around the nucleus only on those orbits in which its angular momentum is the angular momentum of the electron is integral multiple of h by 2 pi, or h is the Planck's constant, where h is Planck's constant. and value of h is 6.6 into 10 to the power minus 34 joule per frequency is joule second. No? E equals to h nu. So nu must be equals to frequency, and E by h nu h will be E by nu. New frequency is going to be 1 by T inverse, right? So E is going to be joule, and this is T inverse. That means that gives me joule second. Okay, this is the of Planck's constant. Correct?
Yes, sir.
Where h is called the Planck's constant. Therefore, that means L is equals to mvr is equals to h by 2 pi. How did I get this? We'll come to this. Nh by 2 pi. How are you getting this one? I will come back to this very soon. Next concept he said. So first concept is the nuclear concept. mvr equals to nh by 2 pi. So this is the first concept, is the nuclear concept. That means there is a central nucleus where the entire charge and mass is concentrated. Then he said an electron revolve around the nucleus as in a orbit. Okay, it cannot stay in every orbit. It can stay only those orbit in which its angular momentum is integral multiple of h by 2 pi. By integral multiple I means n is equals to 1, 2, 3 and so on. Clear? This is called the integral multiple of E1, where you know n by another name called principal quantum number. Principal quantum number, because quantization concept, na? Third one is the stationary orbit. Concept of stationary orbits. Concept of stationary orbits. While revolving in these orbits, while revolving in these permissible orbits, permissible orbits, the electrons does not radiate. Electrons does not, DOES, does not radiate any energy. Okay? Hence these orbits are called stationary orbits. So that means they are neither accelerating, neither they are decelerating. Okay? So hence these orbits are called stationary orbits. Hence the name stationary. Hence they are called stationary orbits. Stationary orbits. Next is, okay, the last one. The last one is frequency condition. What is this frequency condition? That means that whenever an electron is going to jump from higher orbit to lower orbit, it is going to give out radiation, okay, or and when it absorbs some radiation, it will jump from lower orbit to the higher orbit. Okay, while doing so, it releases energy in the form of photon. Okay, the energy of this photon is directly proportional to the frequency. Okay, so what does this say? An electron can jump from an higher orbit to a lower orbit. Okay, higher orbit to a lower orbit. When it does so, it releases energy. It releases energy. It releases energy in the form of a photon. It radiates energy, or you can say it radiates energy. It releases energy,
Yes, it radiates.
or you can say it releases energy in the form of photons. The energy of these photons, the energy of these photons is directly proportional to the frequency. That is, h nu would be equals to E2 minus E1. Okay? So we can say also that if you find this definition is too long, you can also say, this would be better in another way, you can write that an atom, you write this portion will be better. An atom can emit or absorb radiation in the form of discrete energy packets known as photons, okay? Photons only when an electron jump from how do I say this, higher to lower, from higher to lower, or from lower to higher. Okay, so whenever they are going to give this energy, it will be in the form of photons. Whenever they jump from lower to higher or higher to lower, it is going to give radiate energy in the form of photons. The energy of these photons is directly proportional to the frequency. Clear?
Yes, sir.
So h nu is equal to E2 minus E1. This is what we were saying. Where E1 is the energy associated with the one orbit, and E1 is associated with the another one. Okay. So this is the concept of the Bohr's quantization. That means if I have this nucleus, this is one orbit, this is another orbit. Okay, so when an electron jump from this, if you give some energy, it is going to jump from here to here, and that means you have to give some energy to it. When you give some energy to the electron, it jump from this to this, from inner orbit to the outside. And when the opposite happens, when electron jumps from higher orbit to lower orbit, it is going to give out some energy, which would be h nu. Okay, so this is the E2, this is E1, then this is E2, and in the opposite case, this would be E2, this would be E1. Okay, so it's like that. Sometime it will absorb and sometime it will radiate, emit. Clear? So this is the quantization concept of Bohr's atomic model. Now let us understand this with the help of a hydrogen-like atom. Okay? Bohr's concept applied to an hydrogen-like atom. Let's see. So in a hydrogen-like atom, what do we have? We have a central nucleus, and then we have, hydrogen is simple one, simplest atom, we have a hydrogen-like atom, we have a nucleus, and we have a single electron orbiting around the nucleus. Correct? The distance between this and this, let's say this distance be r. The electron is moving a circular orbit. So this is its velocity v, drawing tangent at any point will give you the velocity. And the nucleus, the charge on the nucleus is Ze, and the charge on the electron is E. Correct? So,
Yes, sir.
according to Coulomb's law, for this, according to Coulomb's law, force between the nucleus, Coulomb's law, force between the nucleus and the electron, what do you think it would be? It should be, force would be equals to K Ze into E by R square. This is the magnitude of the force. So that you see that minus E is not been there. So Ze E square by, that is K Z E square. Now if this body, if the electron is moving in a circular orbit, that means this force is responsible for the centripetal force. Correct? So this force is responsible for the centripetal force. That means mv square by r must be equal to k z e square by r square. You can cancel this. So I get here r equal to k z e square by mv square. Correct? Now according to Bohr's quantization, condition, electrons are allowed only those orbit in which orbit is integral multiple of mvr. So that means L, angular momentum is mvr, must be equals to nh by 2 pi. Okay, how this is coming, I will come back to this relation, don't worry. So now, so that means I must substitute this value of r here. So mv and then k z e square by mv square is equal to nh by 2 pi. So this get cancelled, get cancelled. You can see I can find the value of v from here. So v must be equal to 2 pi kz e square by nh. Correct? This is the velocity. This is the velocity of the, I have found the velocity. Now found the velocity, what should I do now? I should now find r once again, because the expression of r do not include the quantization condition. nh is principal quantum number is not present there. So I can easily substitute value. So this is our equation 1, this being our equation 2. So substituting, I can substitute this. Why I have to do that? Because you see r do not include what? The quantization condition n. Okay, the principal quantum number is not involved in r. In case of v, principal quantum number is involved. But in case of, so if I ask you what is the velocity in the second orbit, you won't be able to say. What is the radius of the second orbit, you won't be able to say, because n is not involved in it. So we must bring in the r. So that's why we have to substitute it. So how do you do that? So you bring in there, substituting 2 in 1, I get that r equals to kz e square by m 2 pi k z e square by nh whole square. So that gives me kz e square by m 4 pi square k square z square e to the power 4 by n square h square, which I can again write properly as, so you can see this k and this k cancel, z cancel, e square get cancelled. Correct? I get here 1, I get here 1. Okay? Anything else getting cancelled? No.
No.
So then what can I write here? Then I can write this as n square h square by 4 pi square 4 pi square m
Yes, sir. M.
k z e square. So this is the value of velocity, value of radius, this is the r. So n square h square by 4 pi square m k z e square. This is the expression for radius. This is the expression for the radius, radius of the orbit. You can see principal quantum number is involved. Now we have got this. So what do you think will be the kinetic energy now? We need to find the total energy associated with the electron. So let us go individually. So we can also find out the kinetic energy first. So kinetic energy of the electrons will be what? Let's see. So Ke will be equals to half m v square. So what is m? M is definitely mass of the electron, correct? K, you know that 9 into 10 to the power 9. Z is the Z would be the your number of protons, correct? And then
Yes, sir.
let's see. So what is V then? V will be, V is 2 pi. So half m 2 pi k z e square by nh whole square. So that gives me half m 4 pi square k square z square e to the power 4 by n square h square, which we can do it right properly as, we can see 2 get cancel. I get here 2. So kinetic energy becomes so yeah, so kinetic energy will becomes, now simplify it a little bit properly. So 2 pi m 2 pi square m k square z square e to the power 4 by n square h square. This is the kinetic energy. Fine. Next what? So kinetic energy, you have got it. Potential energy. So potential energy of the electrons. So what is the potential energy of the electrons? Let's see, or potential energy of the system. That means how much work do you have to do to bring the electrons from infinity and put it on this orbit. And you can see these orbits, can you understand that these orbits are nothing but equipotential surface only. So when they are moving on this surface, no work is done. But when they go from one equipotential surface to the next surface, some work has to be, or some energy has to be spent. Is it or not?
Yes.
So the same concept apply here. So that means potential energy will be what? So potential energy must be equal to U equals to minus K Z E square by radius R, correct? So minus K Z E square, what is R? R will be, we have already found R, n square
H square.
h square by this other 4 pi square m k z e square.
E square.
So if I simplify this little bit, so I get here 4, first of all 4 pi square m, then there is a k, so k square, then there is z, so that gives me z square, then there is e square, so that means e square, that should give me 4 divided by n square h square. But wait a minute, this is a minus. Okay, why minus? We have discussed this concept in electric potential. Why minus? Because
it's going from.
Because you have to perform, no? Is it or not? So the system, if you want to break this system, what do you have to do? You have to supply some energy, right? So that thing.
If we we're giving energy, that will.
So this is the potential. If you want to break this system now, you must have to supply some energy in order to take it out. Correct? Is it or not? So then, so what will be total energy then? Let's see. So total energy in this case will be, so the same concept which I have discussed with you in electrostatic potential energy, same thing only. Okay? So remember that there's an external force and there is the force due to the electrostatic force of repulsion. The same way, the same all those things apply out here. So let me finish with this first. So total energy will be then kinetic energy plus the potential energy. Okay, so kinetic energy will be how much now? 2 pi square m k square z square e to the power 4 divided by n square h square, then minus 4 pi square m k square z square e to the power 4 by n square h square. So let's see if in one go we have been able to do it properly. I can take what common from here? What can I take common out from here? Can you tell? I can take, you
2
see,
pi square.
I can take, what I can do, you see everything is there, common, pi square is there, m is there, k square is there, z square is there, e to the power 4 is there, n square is there. So if I do like this, if I multiply and divide by 2 in this equation, so this become, what will this become? 2 pi square m k square z square e to the power 4. So this is a checkpoint. If you have done everything correctly, then you should get all these terms correctly. If you have done any mistake, you have missed one term. You'll see many reference book, they will break this k and make this even more complicated, 1 by 4 pi epsilon. No need to break the k in here. So then I get here 4 pi square m k square z square e to the power 4 by 2 n square h square minus 4 pi square m k square z square e to the power 4 divided by n square h square. Now can I take everything common except half and minus 1? So I will take everything common. So 4 pi square m k square z square e to the power 4 by n square h square I take common and I get here 1 by 2 minus 1. So this gives me minus half. So I should get here 4 pi square m k square z square e to the power 4 by n square h square, then minus half, correct? So this 2. So I get here, so I'm going to get here total energy. The expression for the total energy now becomes minus 2 pi square m k square z square e to the power 4 by n square h square. This is the expression for my total energy. Okay?
Yes, sir.
So you can see, look at this expression and the expression of the kinetic energy. 2 pi square m k square z square e to the power 4 by n square h square. That means this was the potential energy of the system and this is the total energy.
Total
So
energy.
this total energy is nothing but equal to the kinetic energy minus of kinetic energy. This means what? The total energy of an electron is completely kinetic. The energy of an electron, in an orbit is completely kinetic. Means it is not at rest at all. It is constant motion. We can interpret it like this also, no? Completely kinetic. Okay? Now, if I solve the constant, so let's see what we know from here. So I see that pi equals to 3.14. A mass of electron is equals to 9.1 into 10 to the power minus 31 kg. Okay? K equals to 9 into 10 to the power 9. Okay? 10 to the power 9. What was this unit? F is equal to, remember, F is equals to K, Q1, Q2 by R square. That means it is what? Newton meter square
inverse
per coulomb inverse. Coulomb square per coulomb square. So that means Newton meter square per coulomb square. Correct? Then what else is there? So this is written Z. So Z is we're going to take the value of Z to be for using the constant. Now Z, how much I said was Z? Z would be I'm doing some mistake. So it was
Mistaken.
so. Just a minute. How come I forgot the Z? Z equals to 1. Yeah, sorry. Come on, so silly of me. So Z equals to 1. So hydrogen. Sorry, Z equals to 1. N equals to, if I take this as 1, and what else? E equals to 1.6 into 10 to the power minus 19 coulomb. And H, I have already told you, 6.6 into approximately minus 34 joule second, right? I get this thing to be total energy. I'm writing this now E. Let me not take this as 1. Let me keep it as N only. Let me not keep it. Okay? Let us keep it. No need to take the N. So I will get this. Everything else is a constant. If I solve this, I'm going to get En. That means energy associated with an electron in nth orbit is minus 13.6. That means whole these things constant comes out to minus 13.6 by N square. Now electron volt is also. I have to give it in electron volt. This is in electron volt. Okay? So this thing is coming in electron volt. EV. Okay? That means that 1.6 into 10 to the minus 19 coulomb is still there. We're keeping it in EV. Understand? So using that, I get the value to be 13.6 into 10 to the minus 13.6 by minus 13.6 by this square. Okay? So, may I clean it? I think I have written a lot.
Yes.
So,
Yes.
now what can I write is that, so we see that En is equals to minus 13.6 by n square, EV. Now the negative sign implies energy has to be spent. Energy has to be spent to remove an electron from the orbit to make it free from the nucleus pool, right? So we'll not stop here. Let us keep carrying on. So now we see that En is equal to minus 13.6 EV by n square, correct? So for n equals to 1, that means E1 is equal to minus 13.6 EV. This level, that is the lowest level, this level is called the ground energy level. Ground energy level. Now I will be drawing one diagram with it, along with it, ground energy level. So let me draw a diagram showing you the energy levels along with, this is the diagram of the energy levels. Let's see. Okay, and different energy levels will keep forming. Okay, so the ground energy level is the minus 13.6 electron volt. This is the ground energy level, correct? Now, and the ground energy level is what? So it is the most closest. This is the closest to the nucleus, closest orbit to the nucleus. And beyond that, everything becomes the first excited state, second excited state, and so on. Clear? So now,
Yes, sir.
so you have to supply some energy to remove them. Now if I take for n equals to 2, so if I take n equals to 2, so E2 will be now how much? Minus 13.6 by 2 square. That is minus 13.6 by 4. How much is it now? Tell me. Divide that and tell me how much is it? Divide that, n equals to 1. So 13.6 divided by 4, roughly, I should get here 13.6 divided by 4. So 4 3s are 12 and 4 4s are 16.
16.
That means minus 3.4 volt. minus 3.4 electron volt.
3.5.
Electron volt. So this is the energy associated with the first excited state. Okay, energy associated with the first excited state. So that means how will I draw this now? I'm going to draw it here. So this is my first excited state. This is n equals to 2. So this is minus 3.6. Sorry, how much? Yeah, 3.4. 3.4 electron volt. What about the second excited state? For n equals to 3. For n equals to 3, E3 will be what? Minus 13.6 by 3 square. What will I get? 9. So minus 13.6 divided by 9. Divide me and tell me how much is it.
Point. So then 13.
How much is it? Tell.
Yes. 4.
So it is how much?
So 1.5.
Minus 1.5.
Yes.
Minus 1.51 I think electron volt. So can you see the energy gap? This is the energy. This line. The y-axis line is the energy. So if this is 13, so this is a huge gap. But this is less. So can I draw somewhere here maybe? Somewhere here I will draw. So this is my minus 1.51 electron volt. Let us draw the next level. N equals to 4. N equals to 4. E to the power 4 will be how much? Minus 13.6 divided by 16. How much? Tell me. How much is it?
Wait, divided by 16. 0. Point.
How much? I don't have calculator, neither I have phone. So
Oh, so approximately 0.85.
0.85.
85.
Yeah, correct. So it is approximately minus 0.85 electron volt. Now notice properly. The diagram which has been shown in the book, we are actually drawing that. But we are drawing it mathematically. So this is minus 1.5. That means 0. So you can imagine. So this is 1.5. 1.5 is maybe again little bit more. So we can draw perhaps somewhere here maybe. Would be the gap. So this is our minus 0.85. Then again after that n equals to 5. N equals to 5. So E5 will be how much then? Minus 13.6 by 5 square. That is 25. Will be how much? Tell. How much?
0. So 0.54.
0.54 minus 0.54 electron volt. So again you will draw this. So you can understand and so on. It continues. So actually we need, because we're going to see that n1, 2, n equals to 3, n equals to 4, n equals to 5. We need one more. So n equals to 6. So these are different excitation states, right? So n equals to 6 now. Last one, you tell me. E6 is how much? Minus 13.6 by 36. How much is it? 0. 0 point, how much? I think it would be 0.36. So 0.3 something maybe. Minus 0.3 probably.
36.
3 3s are 9, yeah. 0.36 or 7. I think 0.7 electron volt. Yeah, 0. I think just check it once. 6 or 7 electron volt. So that means here is my line.
No, that's the 0.37.
So this is 0.37 electron volt and so on. So this is my n equals to 6. So we have drawn this up. This is the energy level diagram of this is the energy level diagram of hydrogen atom. Because we're doing energy level now. So energy level diagram of hydrogen atom. Now what happened? When an electron is going to jump from one energy level to the another, what is going to happen? Now let us see that. Okay, so now guess what? So an electron, so if you supply, so let us come back to the equation. You have to tell me the equation of the E, energy. You have to tell me the equation of the because from there we're going to find out what is the spectral series. Okay, you have to tell me how you derived that equation, or tell me about let us look into the line spectra of hydrogen atom. Line spectra. We'll come to the line spectra now. So now, so you have seen. May I clean this now, because
Yes, sir.
I will be needing this once again. So now, okay, let us clean it once again only. Now, let us look into the line spectra of hydrogen atom. Now, how do you do the line spectra? So tell me the equation of the electron, the energy, En. Not that minus 13, but before I solve it, what was the value? What was the value? How much was the value of that?
Of what, sir?
En equals to how much? What was that? I found it minus, I think minus something it was. Just a minute.
So minus En is equal to minus 13.6.
No, not that. The full expression. 2 pi square, then something was there, m, I think m, then how much? Total energy E equals to minus 2 pi square m, something was that, k square e to the power 4, I think, pi n square h square. Just check, is n square h square, n square, yeah. So now n square h square. Now you imagine an electron jumps from, suppose an electron jumps from higher orbit, let's say higher orbit to a lower orbit, that is, then we know what, whenever it's going to jump, it is going to release according to the last one. That, remember that frequency concept, whenever electron of the Bohr quantization condition, whenever electron is going to jump from higher to lower, it is going to give a radiant energy in the form of photons. That
Yes,
means
sir.
h nu must be equal to change in, let's say, E n2 minus E n1, correct? From En2 to En1. So that means what it becomes then? So this one will become minus 2 pi square m k square e to the power 4 by n2 square h square, okay, minus, plus it becomes plus now, 2 pi square m
So plus what? Oh, okay, ma'am.
k square e to the power 4 by n1 square k square. Can I write like this? I can take everything common. So what will I get now? So I'm showing you, let me draw one diagram here. So if this is the nucleus, this is one orbit, this is the ground state, then this is the first excited state, that means n equals to 2. This is the second excited state. This is the second excited state of hydrogen atom. Now an electron jumps from, this is an electron, it jumps from here to here. That means it jumps from n equals to 3 to n equals to 2. Okay? Or I can write this is my n1 and it jumps to n equals to 2. So when it does so, it is going to give out radiation like this, h nu, right? So then what can I write? Then can I take everything common from here? So I can take 2 pi square m k square e to the power 4 by, this is h, no, sorry, this is h, by h square. I can take common out from here and I will get here 1 by n initial square minus 1 final square, or n2 square, right?
Yes, sir.
Initial to final, because this is minus, so n2 is minus and n1 is plus, so just switching it. So now we know what. So frequency h nu can be written as c by lambda, which is equals to 2 pi square m k square e to the power 4 by h square, correct? Or 1 by n1 square minus 1 by n2 square, right? So we are looking for that wavelength. So whenever it jumps or whenever it absorbs, remember that absorption spectrum. So it is happening here. When an electron jumps from higher to lower, it gives out energy. Okay. So what was there when it was in case of when the gas was discharged? When a gas discharges at low pressure, that is emission spectrum. What do we see? That when you discharge a gas at low pressure, it is going to give out the radiations, right? And we will see in the spectrum that there is a what? There is a what? Bright lines on dark backgrounds, correct or not?
Yes, sir.
So some colors are there, is it? So we are in that region now. So what is that wavelength? What is that when you discharge it? That means when you discharge it, that means what is happening? What is it releasing? What is it releasing? So what wavelength is that? We are looking into that. So then I can write this 1 by lambda is equal to, so we can write this as what do you call that? Sorry, we can write this as, so 1 by lambda is equal to 2 pi square m k square e to the power 4 by ch cube 1 by n1 square minus 1 by n2 square. Now this is all the values on this, all the terms on this equation are constant. So you can write this as 1 by lambda is equal to what? R, or known as Rydberg constant, R, or known as Rydberg's constant, minus 1 by n2 square, where R is called where R equal to 2 pi square m k square e to the power 4 by CHQ is called the Rydberg constant. Rydberg's constant, understand? So, and its
Yes,
value,
sir.
you can put it all the values. C is the speed of light, okay, and H is Planck's constant, M is the mass of the electron, K is 9 into 10 to the power 9 and 9 to the power 9. So if you solve this, you're going to get this close to 1.07 into 10 to the power, how much was it? 10 to the power 8. Let me check it once, per meter. This is the Rydberg constant, okay. Let me check the value. Rydberg constant,
Constant.
it is 1.09. I'm saying 809 into meter inverse. Here is the formula. Yeah, it's correct. So 1.09 into 10 to the power 7. Sorry. Yeah, that is a different. It is 10 to the power 7. 08 into 10 to the power 7 per meter. Sorry, yeah. So 1.08 into 10 to the power 7 per meter. This is the Rydberg constant. And look at the expression here. M e to the power 4 8. Why is that 8 pi 8 epsilon is coming? Don't get, no, you break this. K equals to 1 by 4 pi epsilon naught.
Oh, okay.
I'm not breaking that. I'm not breaking that. So they have break. So we can break it. No problem. 2 pi square m 1 by, now 1, and that is e to the power 4 by 4 pi epsilon naught c h cube. So pi get cancelled. 2 2s are 4. 2 is pi square. So it should be pi m e to the power 4 by this give me 8, somewhere 8 epsilon naught 4
8 epsilon naught H.
where is it? Oh yeah, that means you have to break this right from the beginning. So it is not that, you just need to
So,
break.
but even if we break it, then so down to they're giving us 8 epsilon naught. But when we open K, then that becomes 1 by 4 pi epsilon naught.
Just a minute,
Then
let me see where is the mistake I have done. 8 epsilon naught, now 4 2s are 8. So where is that? I think, yeah, you have to come from the, it was square. It is K square. It is K square. No.
okay.
So this becomes how much? 16 pi square, sorry. So let me clean it once again. So actually these things can be done from the beginning only, but I did not. It makes it more complicated if you break the
Yes, sir.
epsilon naught in the beginning only. So R will be then 2 pi square m e to the power 4 by 16 pi square epsilon naught square c h cube. So pi get cancelled, okay, and there is a pi,
Then 2 8.
no pi, yeah, correct. So then 2
So, but we're still left with pi.
8, no, there is no pi, and then, yeah, we have got it. So m c m e to the power 4 by 8
8
epsilon naught c h cube. This is h cube.
So it's
Epsilon square
square.
c h cube. No. Cube. Be careful. It is h cube. Okay. So that means this is our Rydberg formula. Done. Now what does this help us? How does it help us? So Rydberg formula 1 by lambda. Let's see what is it. So this is our, now whenever electron is going to jump from one particular orbit to another, it is going to give me different lines. Correct? So may I clean this now?
Yes, sir.
May I clean it? Let me clean it.
Yes, sir.
So now, so the energy level, so let us look at these diagrams now. So this is our nucleus, this is our first orbit, second orbit, third orbit, okay, then fourth orbit, fifth orbit, I'm drawing so badly, you can draw it with a You can draw properly 5th, and this is 6th. Okay? So this is the 6th orbit. So this is the 6th orbit. So now what to do is this. So this is our nucleus. This is our central nucleus. Right? Now first is 1, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Fine? So now
Yes, sir.
whenever an electron is going to jump from, let's say, first one, 1 by, so the formula is 1 by lambda equals to what? R 1 by n initial square minus 1 by n f square, final square. Right? So let us draw one more diagram here simultaneously. So we are looking at the emission spectrum, not the absorption. Means it is releasing energy, it is radiating energy. So let's say an electron jumps from n6th, correct? So tell me in which case it is going to release maximum energy. Now look at this equation here. It's a very important. E is equals to h nu, right? And it can be written as E2 minus E1 or E final minus E initial, right? We can write like that, correct? So we are looking into the, when it is jumping, when it is falling down. So look closely what is important here for us. So frequency, so you can see energy is proportional to frequency or hc by lambda. So energy is inversely proportional to lambda, correct? So tell me in which case the electron is going to release more energy. Is it from n equals to 2 to n equals to 1, or n equals to 3 to n equals to 2 to 1, or n equals to 3 to 1? You see, if the energy is less, wavelength will be, and also frequency is proportional to 1 by lambda. Look into these three fundamental differences here. Okay? So if energy is less, wavelength will be long. If wavelength is long, frequency must be short. Right?
If wavelength is long, frequency should be short. Okay.
Okay? Now let me draw the electromagnetic spectrum also here. I will teach you how to do this later. For now you know that first thing, it starts with the band is like this. First is the radio waves, then is the microwaves, then is the infrared waves, then is the visible light, then is the UV rays, then is the X-rays, and then finally is the gamma rays. I will teach you how to write all the frequencies and bandwidth just looking into this. Okay? So now you see, if I increase, if the wavelength increases, correct? Now if the energy is less, wavelength is less, wavelength will be more. Energy and wavelength inversely. If energy is less, that means when an electron is going to jump from n equals to 2 to n equals to 1, come on, green color, from n equals to 2 to n equals to 1, it is going to give me less energy, right?
Yes, sir.
So this is my first orbit here.
Yes, sir.
This is my first orbit. So how much was it? This is minus 13.6, correct? And
Yes,
how much was this one? Please tell me that from the table. It was how much? Minus 1.5, no? Minus 8 point something.
What? So which one? The first one minus, no sir, 3.4.
13.6, then how much is it? First line.
It's 3.4, no sir.
Minus 3.4, okay. So minus
Minus
3.4. That means when an electron is going to jump from here to here, that means from n equals to 2 to n equals to 1, which I am showing you here, it is going to release less energy. If the energy is less, wavelength has to be more. If the wavelength is more, frequency has to be short. Now you look at the electromagnetic spectrum. this side, if you go this side, wavelength is very long wavelength. Okay, wavelength is long means frequency is short. Okay, wavelength, radio wave is this side is long wavelength. As you go this side, wavelengths, what happens is that frequency increases as you go from,
And
correct.
yes, sir.
So radio wave has the longest wavelength. So if you're going on the right, from, I'm talking about the visual, this is my reference. If you go this side, wavelength is going to increase, and if you go this side, if you go on the left, wavelength will fall. Now the opposite you think about it,
Frequency will increase.
and now you think about it. Okay. So this is the trend of the radio wave. So radio wave has the highest, longest wavelength, and the gamma rays has the highest frequency. You got it? So wavelength is short. So this is my reference. This is less lambda, this is more lambda. Fine. So now you see ni square minus nf square. So 1 by lambda is this. So that means this radiation is what? This wavelength is what? The frequency of this radiation is less. It is falls on the infrared region. Okay. So for n equals to how much? From where? From your initial should be. That means whatever be, you are coming to the n equals to 2. So what you should get? You should get this to be the Lyman series. I don't know, n equals to 1. Correct. Your final be whatever be it. Initial n1 is ni. This initial is always 1. From whatever orbit you come. Okay. So whichever orbit you come, it is going to be what?
1.
It is going to be, so n2 would, n final will be n2 will be, that means n initial is always what I'm saying, anything mistake I did? No, I think no. Yeah, you're coming to n, sorry, I think it is please check one. I think it's n final. Yeah, it is n final minus initial. No, yeah, it will be n
F minus N.
nf minus n1. Okay, nf minus, sorry, yeah, it should be nf minus n1. Okay, because we are releasing it. You're coming from initial to final. Please check there. I think there's one mistake maybe. Please check in there once.
Here you're written final minus initial only.
Yeah. It's final minus initial only. Yeah. So n2 would be then, and final. So nf would be always your 1, and you have to let it jump from any orbit. Maybe from here to here. Maybe from here to here. So you're always coming to 1, first orbit. Clear? So this is the one. So next line is what? After minus 3.4, tell me the lines please fast.
The values, sir.
Yes.
1.51
51
and then minus 0.85
minus 0.85, then
minus 0.37
minus 0.37. All of them? 1, 2, 3, 4, 5. One more is there? No? No.
No, sir. Till n is equal to 6.
Okay, no problem. So
Huh?
n equals to
1, 2,
1.
3,
Yeah, you're
4,
missing
5,
something.
Yes, so 1, I think I'm missing something. 1 and 2.
0.54 you are missing. 5.4 you are missing.
Oh, sir, I think you forgot to write the value, sir.
5.4 0 minus 0.54, and then finally the last one will be they are quite close, minus 0.36 electron volt. Okay.
Yes,
So
sir.
then,
Yes.
so when it jumps to, so it is based on which level is it jumping, correct? So you can see that. So first one, whenever n1 is equals to it is jump from higher to lower or whatever way, this would be in the infrared region. So this is another one. This is the second. This is the H alpha line, H beta line, H gamma line, and so on. You can write this H alpha, beta, gamma, delta, so on. So like this. This is which series? This is the Lyman series. This is the Lyman series, correct?
Yes, sir.
Now you compare. Let me finish it, then I will tell you about the spectrum. So this is the Lyman series. Okay. So n equals 2. Then how much? N final must be 2. Final must be 1. N initial can be anything. 2, 3, 4, so on.
Okay.
That becomes my lambda. So that means 1 by lambda must be equals to R 1 by initial. So it is 1 by 1 square minus 1 by n square.
2.
Now for n equals to 2. Okay?
Balmer series.
N final equals to 2. I have done this earlier, and this is
Yes.
anything. N2 is anything. 3, 4, 5 from wherever. That means I am talking about this one now. It falls on this now. Okay?
Yes, sir. So that now I get it. Yesterday, like the questions that we did,
Yes.
which was 1 by 2
So
square.
that means
those
it is
were
false. Now
the
wait a minute here. More deep you go, the energy is more, no? And you are one level out. Definitely energy will be less.
Yes,
So
sir.
this must be in the after infrared. So this is in the IR region. No, sorry, what I'm saying. This is in the UV region, ultraviolet region. Okay? This is in the ultraviolet region, UV region. Because more energy,
Yes, sir.
and then you can tally on this thing, whatever laws I have given. From there you can see the frequency will be very high. High energy, more energy means high frequency. Simple. So that means this must be UV region. This is UV region. Lyman is in the UV region. Next comes the Balmer series. So Balmer series, it jumps from minus 1 point to this, then from here to here, here to here, and so on. This is Balmer series. So this is in the which region? Balmer series. This is in the visible region.
Okay, visible region. So, sir, means out of all the spectral lines that have been discovered, only Balmer series falls in the visible.
I showed you the pictures. That's why you could see it.
So, yes, sir. So only that, right?
Yes.
Only Balmer series.
So this is in the VR region, visible region. The next one, after Lyman, Balmer, Bastian. Then is the Paschen series. So in the Paschen series, so this is next one. I will write this as it will come to the from anywhere to here.
So one you missed. So in
Yeah. Sorry. Okay. Finally, so this is Paschen. This is, I'm not missing anything, no? Paschen.
No, sir.
After Paschen comes the bracket. So you can now draw, rest of it you can draw it. You can finish this diagram.
So good.
You can finish this diagram. This one, sorry, I have missed.
Less space.
Okay, so this was the Lyman. This is Balmer. Then after Balmer comes, so I come to this one. So let me use a separate color now, blue color now. It should be like this, like this, like this. Okay, 1, 2, 3, correct. Next one will be, so this is Lyman Balmer, this is Paschen,
Paschen.
then there will be bracket,
Brackets.
this is the bracket. So what did I do? No, yeah,
Correct, sir.
it will come from, not from there, it will come from here. Bracket,
Oh.
bracket series. Finally the last one would be the P-Fund
P-Fund.
series. So this is the P-Fund series.
P-Fund.
Okay, so Paschen, and then I will have here, so this is done, no? N equals to 1, n equals to 2, done. Now n equals to 3, so for n equals to 3 I think I have done, no? Paschen done. So n equals to 4, so for n equals to 4 it should come here and here. So this is our bracket, which is again in the which region? So tell me one thing, in this case what will happen? These are small, less energy will come, frequency is less. Frequency less means wavelength is long. So they must be in the right side of the visual, a VL, of the visual light, na? Visual spectrum. So that means these are all in the infrared regions. These are all in the infrared regions. Similarly, the last one, which will also is the P-Fund series. Correct? You can draw one more level here and do it here. So this is the P-Fund, which is again in the IR region. So you see, this is how we have drawn. Isn't these diagrams are present in the book?
Yes, sir.
So
Should be.
so you can easily write rest of it from here.
Yes, sir. I'll do.
So you can see now 1 by lambda would be equals to R, 1 by 2 square minus 1 by n square. This is Balmer. This is Balmer. Next is 1 by lambda equals to R, 1 by 3 square minus 1 by n square. This is Lyman Balmer. Paschen. Then 1 by lambda equals to R equal to 1 by 4 square minus 1 by n square. This is bracket. Finally 1 by lambda equals to R, 1 by 5 square minus 1 by n square. This is P-Fund.
Sir, I had one question.
Yes. So that's it. This chapter is finished.
So yesterday I was just going through the NCERT, for this chapter only. So, like yesterday when we did the sums for H, alpha, beta, when we were taking out those values, no sir. So R we took the constant, we took the Rydberg constant. Rydberg constant we took as 1.08 into 10 to the power 7, no. So in the book this is given as 1.097. So I'm not getting, because I think maybe because of that, but I'm not getting the exact value as it's given in the book.
Okay. No problem. These are approximations. Don't do just mistake with the power. 10 to the power 8 or 10 to the power 7 is a major
7.
mistake. But 1.0809, it accepted in this level. Accepted in this level.
Okay.
And anyway, R will be provided to you. As I am using it, so but it will be provided to you. Okay.
Okay, sir.
That's it. We will discuss few numericals on this. Small numerical, maybe at the most half an hour, 45 minutes. Done. But the chapters, everything is over. Okay.
Okay, sir. Thank you, sir.
Yeah. Okay then.
Okay, sir.